Okay, well, first I would like to thank everyone for joining me for our webinar today on condition testing for mission critical fuels, the key piece of the puzzle. This is a sequel to our August webinar that we did on condition monitoring, which that one covered essential steps and considerations for how to monitor the condition of stored fuels with the goal of preventing and even predicting microbial contamination problems. But monitoring is really only the first part of the puzzle, and that's why we're going to cover the rest of it today. Monitoring, that involves pulling the right kind and the right number of samples, doing it at the right time, and handling those samples properly to ensure that they stay representative of the place that they came from. However, it doesn't just stop there. We have to know what to do with those samples if they're going to tell us what we need to know with respect to, potential problems related to microbes in our storage tanks and our fuel systems. And so that is where condition testing comes in, which is the subject of our webinar today. And now ultimately our goal is going to be to make sure that you understand the best ways to analyze the fuel samples that you get from your condition monitoring efforts. Along with, we want to present the best practice options for solving microbial problems if that testing that you're going to do, if that hints that there might be a problem. So that's our starting point. We've recognized that microbial contamination of stored fuels is probably the number one problem and the number one danger to the health of stored fuels, especially mission-critical stored fuels. So it's important that we take the right steps to give the problem the respect that it deserves. So in our webinar time together today, we're going to start with a quick review of the important best practices that we need to know about condition monitoring. So we're going to review that quickly since we've already done a webinar on that. And we need to review this because proper testing and best practice problem solving, that always starts with monitoring the condition of the fuel. Then once we finish that, we will transition to a discussion of the major testing approaches that are recommended for taking those samples, those condition monitoring samples, and start to get some useful answers on what they're trying to tell us. And these major testing approaches that we're going to discuss in our webinar today are, as you can see on your screen, gross observations, chemical and physical tests, and microbial detection tests. So we need to know more details about each one, why they're valuable, what kind of useful information that they can tell us, and how each one in particular brings us closer to our ultimate goals. If we're going to understand how these fit into what we should be doing with our stored and our mission-critical fuels, we have to know more details about things like that. And then lastly, we will talk about the what we need to do about it issue, which is referred to normally as contamination control. There are options to consider there, and it is important for us to have a handle on what we do and do not need to do there. And of course, just as importantly is the why we need to do these things. So we're going to do our best to ensure that by the end of our time together today, the complicated issues of mission-critical fuel system condition testing and contamination control are at least just a little bit more clear for you. Now, if you have any questions, you can post them in the chat box, or afterwards, or rather at the end of the webinar today, we're going to allot some time for questions. And of course, if you have one that doesn't get addressed during that time, there will be ample ways for you to get in touch with us, because we want to make sure that everybody here comes away with something useful, something valuable today that will help them. So let's set the table here with a very brief discussion of fuel microbiology and of condition monitoring. So in our previous webinar on condition monitoring, we kicked things off by saying that fuel microbiology and condition monitoring and now condition testing and contamination control, they're all areas where the further you dive into them, so to speak, the more complicated you realize that these issues or these areas are. I mean, just even considering the fuel microbiology piece, there are literally 1 trillion species of microbes on the planet Earth, and we have only really identified about 10 million of those. Consider facts like the average person has 100 trillion microbes living on their body at any one time. The average milliliter of drinking water, every drop of drinking water, contains between 10,000 and 1 million microbes. And then if you zoom that in more specifically to the tank bottom water, the water you find in fuel systems, well, every milliliter of that can contain between 1 million and 1 billion microbes. So really, it's a microbial world out there, and we're just living in it, basically. And once we realize this, it should never then surprise us to find microbial contamination pretty much anywhere, especially not in fuel storage tanks and fuel systems. So how do microbes get into fuel systems? Well, there are really 2 questions that go into that. How do microbes get into storage tanks, and how do microbes get into the fuel distribution system itself, especially when we've already acknowledged that microbes are everywhere anyway? Now, for storage tanks, there's lots of ways that they can get in there. Basically, anything that enters the storage tank has some level of microbial growth associated with it. Whether you're talking about water, free water ingress from leaks or from spill buckets, even things like water vapor and just dust that's on the air that goes in and out of the vents, and of course, fuel drops. Anything like that, you can have fuel microbiological inoculation, so to speak. Now, the fuel distribution system, for that, of course, that's everything upstream of the storage tanks. And so if we're going to look at that, we have to start at the refinery. Of course, that's the starting point. And we start with the baseline understanding that fuel, when it first leaves the refinery, or when it's first put together, it is basically sterile because of those high distillation temperatures. But it is only sterile for a pretty short period of time, because it's going to go into refinery bulk tanks. Then it's going to get transported by a ship, which uses water for ballast. Pipelines, rail cars, none of those are sterile by any means. They're going out to fuel depots, going to tanks there, which have plenty of microbiological growth associated with them. Then it's sent out, for local and regional distribution. Now, considering that these fuel depots are getting fuel from more than 100 different refineries, and it's aggregating all that fuel together. So if fuel from one of those refineries, from the tanks, and one of those refineries that has biomass growth somewhere or some kind of microbiological growth, it's going to carry that and add it right to all the fuel from those 99 other refineries. And then from the fuel depots, the fuel goes to smaller bulk facilities and then to the end ground dispensing facilities. So through all this, we can see that even though the fuel is sterile when it immediately leaves the refinery, there's plenty of time, plenty of opportunity for it to develop the start of microbial problems on its way out to the final destination. Now, if you take one single, what they call a planktonic microbe that's in the fuel, in the liquid fuel, it only takes 24 to 48 hours for one single planktonic microbe to establish itself on a solid surface and form a viable, complex microbial colony. And in any given storage tank that has a biofilm presence already in it, you're likely to find thousands of different species of microbes, all requiring differing levels of different kinds of things to grow, all depending on each other, living kind of symbiotically to live life to the fullest and do what they want to do. And many of these thousands of different kinds of microbes are doing deleterious things to the fuel and the tank systems that they live in. So with respect to their effects on fuel, well, You have microbes doing things like producing acids that contribute to corrosion problems in the tanks, and also producing these biosurfactant molecules. And the biosurfactants, these are what help create these invert emulsions of water and fuel, which results then in hazy fuel. You will have situations where microbes will actually consume the lighter end hydrocarbons in both diesel, but especially in gasoline, and that changes the properties of the fuel, especially with respect to its vapor pressure and its viscosity. Now, when you talk about the tanks and the fuel system themselves, microbes cause delamination of tank linings, destruction of fiberglass surfaces by fungi. Those kinds of things are what are typically characterized as non-corrosive damage. But then there's also corrosive damage, which involves, metal and metal surfaces. And there are multiple serious avenues of microbially induced corrosion to metal surfaces, whether it involves the formation of, let's say, electropotential gradients and galvanic couples, which can happen when you have biofilm contamination of surfaces. You can have localized pockets of oxygen that develop, which creates kind of an osmotic situation where oxygen will want to move from areas of high concentration to areas of low concentration. When it does that, it can actually get trapped in pockets, especially if it happens around biofilm, which then you get a localized area of a high concentration of oxygen, which leads to the formation of things like carbonic acid, which very corrosive to metal. And you can get not only localized high concentration of oxygen, you can get the same for carbon dioxide as well. So again, this is the kind of thing that you could spend a lot of time getting way down into the details here. But I think you get the picture of what we're talking about. So once we've established the picture of the potential microbial problems that stored fuel faces, we now have to talk about the need to monitor the condition of the fuel in those systems and, of course, how best to do that. So in the previous webinar that we did, we introduced the importance of condition monitoring and the testing that follows from that. And we did this by acknowledging that these problem microbes that we've been talking about, they often go undetected in fuel systems because of either incorrect sampling techniques, incorrect testing methodologies, or some combination of the two. And if you were choosing which one was the biggest culprit, the incorrect sampling thing would be the greater problem out of the two. When it gets down to it, you cannot have valid condition testing, which is the main topic of what we're talking about today. You can't have that if you don't have best practice condition monitoring. And that really was the topic of our previous webinar from back in August. And we don't really want to chew up all of our time rehashing those details, even though there were a lot of details that we could talk about. So what we're going to try and do is summarize the important things to know about condition monitoring in basically like 4 main points here. Okay, important point number one. Number one is detecting microbial contamination starts with sampling. And given that, where you sample and how you sample controls what you're going to detect. So if you want to do sampling right, there are standards that give you guidance. There's ASTM 4057. That is officially titled as the standard practice for manual sampling of petroleum and petroleum products. And this document covers how best to collect fuel samples if you want to do specification testing, like if you want to verify the fuel quality characteristics. The problem, though, is that 4057 does not cover the special issues that need to be taken into consideration if you're pulling samples in order to test for microbes. That is why they created the 7464. And 7464 is the standard that gives guidance for sampling that's intended to be used to do microbiological testing and determination. So these two standards are the ones that give us the best guidance for doing, good sampling. Okay, So that's point number one. Important point number two, surface samples are best, but they're not always practical, which means three-phase bottom samples are our best bet for doing this. Microbes, if they had their preference, they would say they most like to live on solid surfaces within some kind of biofilm. So it stands to reason that if you were doing a sample to try and get the most accurate picture of your tank's microbial content, you would want to try to get a surface sample. However, it's rarely practical to get a surface sample in these kind of tanks. That means the next best alternative, is to get three-phase bottom samples. And these three-phase bottom samples, they contain bottom water, they contain rag layer, that's the biological matrix stuff that's formed at the interface between the water and the fuel. And they also contain what they call near bottom fuel, which is fuel that is typically between 10 and 16 inches above the water phase. Important point number three, every tank is different, which means you can use condition monitoring to identify your own system or your own tank's microbial fingerprint without having to rely on what's applicable to everyone else. What we're talking about here means taking regular samples and testing them for microbial presence. And the recommendation, as we covered in our previous webinar, is sampling 3 times per control interval for your tank. Now, how long is a control interval? Well, it depends on your tank. Since the control interval is defined as the amount of time it takes for microbial levels to reach a problem point in a given tank. And that's part of the reason you do condition monitoring, because you want to see what that interval looks like where you are at. Generally speaking, though, most control intervals will be somewhere between 6 and 12 months, which means for most situations you're going to want to be doing sampling and analyzing 3-phase samples about once every 2 or 3 months. And then important point number 4, how you handle those samples can mean the difference between success and failure. We spent considerable time during our condition monitoring webinar emphasizing the recommended best practices for how to handle field samples if you're doing microbial analysis. Samples for microbial analysis, they are inherently different from samples for testing fuel properties. Fuel property samples, those are not inherently time sensitive, but by nature, samples for microbial analysis definitely are time sensitive. The longer the period of time between when you collect the sample and when you test the sample, the weaker the relationship between the test results, the picture that you're seeing from the test, and the actual picture, the reality of what's in the tank where those samples came from. Now, ideally, if you could have best case scenario, you'd be able to test these samples within 4 hours. But we all know that that's rarely practical to do that. So in addition to doing things like making sure that your fuel samplers and equipment are sterile and using unused fuel sample containers to put your samples in, you want to take your pulled samples, you want to get them on ice and then into the refrigerator if there's going to be any significant amount of time between when you draw the sample and when you can test them for microbes. So that's a very basic summary of the important practices in condition monitoring. And that should naturally lead us into the primary topic of our discussion today, which is condition testing. Now, to this point, we know a lot more about microbes, how they grow, what they do, and how they do it, the importance of good sampling techniques and good handling of those samples, and how to accomplish that. We're a lot further along with respect to best practice condition monitoring than we were when we started. So now that we have our samples, we transition into the getting them to tell us the right story. Now, in order to get them to tell us the right story, we have to ask them the right questions. And you use sampling of fuel systems to conduct condition monitoring with the assumption that your samples are an accurate representation of the place they came from. In other words, that they're reliable enough that they're going to tell you the right story if you ask them the right questions. But now we have to determine what our samples can tell us. And this means testing the samples and then interpreting the results. Now, there are lots of different kinds of tests that we could do. Not all possible tests will give us the best kinds of answers that we need. So, what are the right questions? What do we need to be trying to figure out here? Well, from a fuel microbiological standpoint, the questions are going to be along the lines of, do I have microbial contamination in my storage tank? How much microbial presence or contamination do I have? And is, whatever I have, is the presence that I have contributing to existing problems? Or how likely is it to do so in the near future? Now, those three questions may seem to be related, but they're not all answered in exactly the same way. And that means we need to know the right testing approach to take if we are going to best answer them. So these are the kind of considerations that go into what fuel microbiologists refer to as condition testing. Now, there are 4 broad categories for condition testing that we need to consider. First one, gross observation, as you can see on your screen. Second, physical tests. Third is chemical tests. And last but not by any means least, microbiological tests. So let's delve into these categories and talk about what kinds of tests go into them and what roles or what value these tests or these categories of tests may have towards helping us answer the right questions that we're going to be asking. Now, as we said a minute ago, there's lots of tests we can do. Some of the tests involved complicated or I'll say rigorous ASTM lab protocols. They use specialized equipment, specific procedures. So there's plenty of good, valuable tests that fall into that designation. But to start with, we're going to start at a more simple level. That would be the observations that we can make with our senses. That's what goes into gross observations. So we look at the fuel sample. Does it look differently than what it should look like? That's obviously visual. Are there characteristic odors to that? Does it smell like it should, or is it different? That's a gross observation. If you have a filter media and you see that there's some kind of coating on it, you feel the coating. Is the coating, a dry particulate consistency, or is it slimy and slick and shiny? Depending on what your answer is, either one of those can hint at one kind of possible problem versus another kind. So over time, even simple sensory observations of good samples can yield valuable information about whether something's going on that really shouldn't be. Now, one caveat to consider with gross observation testing is the question of how or even whether these kind of observations can be standardized. See, one person's interpretation of how a fuel sample smells can be a little bit different than somebody else's. So, given that recognition, if we recognize that, we have to ask, what, if anything, does this imply that we can or should do? Well, first of all, these are valid considerations. Gross observation tests have what we would call limited replicability. Or maybe it's reproducibility. I'm not sure, but anyway, that just means similar to what I was saying a minute ago. That something, the way two people say something looks, one could say it looks slightly different than what the other person said. So there's a little bit of difference in how two people might assess the same fuel sample there. And that's not necessarily, a problem, so serious of a problem that, invalidates their value. It's just something that we have to take into account in the grand, the big picture of things. But even pointing that out, that's not to say that all gross observation tests are exactly like that. There are some visual gross observations that do actually have some standards that we can point to. Now, when we're visually inspecting a fuel sample, we would point to ASTM D4176, which is the visual inspection for water and particulates. And that actually has two procedures that you can run. Procedure number one, some people in the industry call it the swirl test. You take, I think it's 900 milliliters of sample. Of course, it's in a clear, sample container, and you swirl it so that you create a vortex. And you do that for about 30 seconds, and you hold it up to the light. And when you do that, you or the technician who's doing it will see air bubbles that are going to rise up to the sample surface. But you'll also see water and particulate. If it's there, it's actually going to sink to the bottom. And if there's any visual confirmation that there's water or any particulate, that's considered a failing test. Now, one thing to keep in mind for this is, this swirl test, procedure number one, is most often used in retail settings where they take the dispenser from the pump. Now, it has usefulness there because, if you think about it, pump dispensers at gas stations are supposed to have filtration systems that remove all of the particulate and the water because you do not want any of that reaching the end user. But this vortex test is not as useful if you're assessing bottom samples from a storage tank, because if you're pulling a three-phase bottom sample, then you're going to have water, pre-water, and you're going to have particulate in it. So it's going to be an automatic failing test, which means it does not tell us what we think it should tell us. However, contrast that to procedure number two, which is sometimes referred to as the visual clarity test, and that's what's illustrated on your screen. You have, again, a 900 milliliter sample in a clear container, and you put it up against this bar chart, this bar reference chart, and you see how many lines you can see. And depending on how clear the lines are, it gets a visual clarity score between 1 and 6. 1, which is what you see in the top left, obviously 1's clear. And then you go top left and you move to the right, and then you go bottom right and you move to the right again. And you can see that the bottom-most right picture is a 6, and that's pretty murky, pretty nasty. So this is somewhat standardized because there's a standard that you can create your results from. And if stored fuel does not pass this visual clarity inspection, then that is an excellent indication that there's something amiss that needs to be taken care of. Now, we move now from gross observations of the fuel samples to physical and chemical tests. These are the tests that are done in a laboratory following specific protocols and procedures, and they build upon gross observation testing because their results are replicable and reproducible. If we're doing gross observations, if we start doing gross observations, we can tell that if the appearance or the smell of a fuel sample, if it's not as it should be, then there's a good chance that something's actually wrong. And since microbial contamination is so commonly seen out in the field, we know that microbial contamination is many times a primary culprit for gross observable changes in the fuel quality. We also know, however, that microbial contamination changes the physical and the chemical properties of the test in certain ways. Things like total acid number of the fuel, the peroxide number, the fuel's viscosity, those can all be increased by the effects of microbial contamination, while other things like cetane value and stability ratings, those can be reduced. And none of those are good changes to have happen in stored fuel. So there are physical and chemical tests that we would look at to document and even measure the physical and chemical properties of the fuel as a reflection of the current state of the fuel, as well as possible use for us in trying to predict whether it will change in the future. Now, there are many, many kinds of tests that you can do, but most people don't do many, many kinds of tests. They have limited budgets. They have to pick and choose which tests are most important. Now, in the case of mission-critical entities that are sometimes required by regulatory rules to do fuel testing like this, they typically default to the ones that are required by ASTM D975. D975, of course, we all know is the diesel fuel specification. And so cetane value and viscosity would be two of the physical or chemical tests that are specified in that. But we should also note that D975 does not specify one of the most important physical chemical tests, and those are some kind of stability test. Now you can see on your screen that there are three main kinds. There's oxidative stability, there is thermal stability, and then there's one below it called petrooxy, which is basically like, I don't know, if they took the oxidative stability test and they optimized it for ultra-low sulfur diesel. Now, why doesn't D975 require stability tests? Well, the short answer to that is that stability tests are predictive. They give you some kind of score or measurement that predict whether the fuel sample is going to change condition in the future. Now, despite knowing the importance of D975, of course being the fact that it legally defines what diesel fuel is, it's it's important for us to understand that D975 measures or deals with the current state of the fuel. What is it like right now? D975 is not concerned with the possibilities of what the fuel might be like in the future, because future events are contingent on certain things happening. And so it can't account for those kind of possibilities. It's really outside of the scope of D975 to try and account for that. So despite being predictive, stability tests have a lot of value because they can allude to present-day things like microbial contamination that might be present in the stored fuel and might have contributed to that score being, less than what we would expect it to be. If something has happened to the fuel while in storage, like development of significant microbial presence, well then typically there will be other things that happen along with it, like the development of unstable precursor molecules that are, that if you give them enough time, they will cause changes in the fuel. And that, then the fuel is going to be more likely to change condition in the near future, and thus stability tests can kind of give us an analytical or a quantitative expression of that. Now, we may also do other physical tests to assess the fuel's physical state, and not just simply, assess it in a vacuum, but give us the ability to judge whether these tests can infer microbial contamination right now in the fuel. So there, three of them on your screen right there. Filter blocking tendency. This measures the particulate load that's present in a fuel. And if you have microbial contamination right now, you will have a higher particulate load, right? There's kinematic viscosity, D445. It is important to verify the viscosity of any kind of fuel because viscosity plays an important role in things like is it going to be injected properly? And we also know that microbes consume smaller hydrocarbons in the fuel mix, which can affect the viscosity in a negative way. So if the viscosity is off, then that means that microbial contamination might be something that you might give as a possible culprit for that. Water separation properties, 7451. This test measures the water separability. Some people would say then that you can use that to infer possible microbial contamination, because if you have microbes in the fuel, remember they're going to be producing biosurfactants, and that will cause the fuel to have a poor score on this kind of test. So water separation properties test is another thing that infers that you might have a microbe problem. Carl Fisher water content. It's really an essential tool because it is the industry standard for measuring water content. It does it pretty accurately. You don't need a very large sample. It's a great test. Water content itself does not imply a current microbial contamination, but it does illustrate the presence of something that can help one or make it easier for one to develop or make an actual existing problem worse. Peroxide number 3703, if you have microbial contamination, it will increase the fuel's peroxide number, which then shows up in this kind of test. Same thing for fuel corrosivity, 7548. Microbial contamination makes fuel more corrosive. And total acid number, same kind of deal there. So all of these tests up to now are done primarily on the fuel. But it's also important to know that microbial contamination also affects the properties of the bottom water, the free water, and it does that in a measurable way. This is something that people forget about because they're so focused on what's the fuel like. But a microbiologist knows that it's important to test the water phase if we want to build a solid case that there's a microbial contamination event going on. And we also need to keep in mind that if the water's properties have changed or deviated in a negative way, it typically means something similar has happened to the fuel. So, two tests that are done commonly on the bottom water on your screen. pH. So microbes make both fuel and water more acidic. Now, we measure acidity in fuel by doing a test like total acid number. pH is what's best for aqueous systems like bottom water. Then there's total dissolved solids, 5907. If you have microbial contamination, it will cause elevated levels of dissolved solids to show up in the bottom water. So, to this point, we have covered gross observations of fuel samples that can hint at microbial contamination. And we've covered the physical and chemical tests that give us or can give us a more measured confirmation of the fuel's properties and also the properties of the associated water, both of which can hint at the possible presence of something that might have changed their properties in a negative way. And given the certain properties we look at, we know that these properties change most likely because there's microbial contamination behind it. So that's 3 of the 4 condition testing categories. The last category of tests that we would undertake are the ones that are most specific to measuring or detecting microbial contamination itself, and those are the microbiological tests. Now, this area of microbiological testing options, this is an area where there have been a lot of great improvements made in the recent past. And this gives mission-critical fuel managers much better options for detecting and for problem-solving than their predecessors had. See, back in the day, even if you even had a reason to suspect that there was a microbe problem, the only option you had for some kind of test to confirm it would be you'd have to pull a fuel sample and package it up, and you'd have to mail it to a lab where in about 28 days they'd give you a result back. Now, of course, 28 days is far too long to be really useful because your microbial population in your tank is going to have changed dramatically in those 28 days. But that was the way it was. They didn't really have any better options, which is to say they really didn't have any field options. If somebody who had stored fuel wanted to do their own testing closer to where they were at. Today, fuel managers have a lot more options, and these options all come with their own sets of positives and negatives. You've got culture tests, you've got LFD tests, or LFT, tests, and ATP tests.
Those are the three main options available from at least with respect to being commercially available. So let's run through these and see how these options compare. And as we consider them, we need to consider how the right or even the wrong kind of tests will only give us a fraction of the picture. In reality, all of these only give us fractions of the true situation. It's just a matter of how big of a fraction that we're going to get. See, we mentioned earlier that that it's really important to follow best practice sampling and handling techniques so that we end up with samples that are as representative as possible of where they came from. This is this is most important when you're talking about samples being used to measure microbes. But it's also the area where we may end up with the highest difference between the picture of our sample and the real condition of the tank. And it's important to recognize this, and it harkens us back to what we mentioned earlier about how as it's human nature to assume that whatever samples we pull, they are actually representative of the real situation they came from. People naturally just assume that that is true. Unfortunately, if you pick the wrong kind of test, that can really place a limit on how applicable your test results are going to be in terms of, do these reflect the reality of what's going on in my fuel tank? So these are all important considerations that we have to keep in mind as we assess and compare these different testing options. So let's talk about these tests. We'll talk about what they are, talk about their advantages and disadvantages, talk about their overall usefulness for what we're trying to do. And, what we want to throw in here, the reason why we need to be talking about this is especially for hospitals and healthcare facilities. You have, let's just say that regulatory times are changing. You've got certain documents, or we'll say certain guidelines, like NFPA 110, and they require hospitals and healthcare facilities to do certain things. But up to this point, they haven't been real specific on the kinds of tests that hospitals and healthcare facilities need to do. Well, that's going to be changing. In the near future, NFPA 110 is going to start requiring hospitals and healthcare facilities to do microbial tests and water and sediment tests and stability tests. When will this happen? Could be later in 2019, could be 2020. We're not exactly sure because of the nature of how these things go. And this is going to be a huge change from where, from the current position where both Joint Committee and Children's Medical Services, they both still reference the 2010 standards when it comes to how you should be taking care of your fuel. So these kind of changes are coming, and that's why the kind of stuff we're talking about today is very important to understand. So we start off with the simplest microbe testing technologies, which are the culture tests. Now, we call them culture tests, plural, because there are actually multiple available options that this designation covers. Now, culture tests, these are the oldest microbe tests. They date from virtually, the start of germ theory in the mid-19th century. They're the simplest ones to do because they rely on the ability to regrow a sample or a slice of the system's microbiome using some kind of growth medium. Now, there are four main options for culture tests. Two of these options have ASTM numbers associated with them, and that's good because that means that their procedures have been standardized and vetted by the industry. So, first one, we've got membrane filtration. That's the D6974. This is the standard laboratory test. You take a test sample, you filter it through a membrane that's been filled or inoculated or whatever you want to say. It's been filled with culture medium. And so the membrane catches the microbes, and then you incubate it and you leave it to allow them to grow, and that's how you get your culture. There's Microbe Monitor 2. That is the 7978. And Microbe Monitor 2 is actually what the person with the blue gloves is working with. It's a thixotrophic gel. Thixotrophic is a fancy Scrabble word that means it moves faster when you shake it slowly. But it's a culture medium, so if you inoculate it, it will grow your microbes. Then at the end of the test, you count the number of colonies that you can observe, and you compare that visually to a chart that then gives you a general range of the number of microbes you may have. Now, how accurate is this test going to be? Well, we should be able to quickly realize that the test's accuracy depends on the user being able to both accurately identify the colonies and then, of course, accurately count them. So membrane filtration and Micromonitor 2 are the two culture tests that have ASTM numbers. The third one, Liquicult. Liquicult, also known as non-selective broth, and there's little glass jars, as you can see on the bottom picture, and they contain a dye, and the dye will turn red in the presence of microbes that produce acid. And so you leave it for X amount of time, and then depending on the color that it is after X number of days, you can estimate the extent of microbial presence from your sample. Of course, source of error for that could be that maybe one user thinks that it's this shade of red or this shade of orange, and another person says, no, it's this shade of orange. So there is possible deviation in interpretation of the test, but that's what a Liquicult is. And then there's what they call BART tests. I don't know what the acronym BART stands for, but BARTs are similar to Liquicolts. They're packages of multiple bottles, and which are filled with growth medium, and they enable you to be more specific in the kinds of microbes that you're detecting. Because each different bottle, and I want to say there's 10 bottles in there. I could be wrong about that, but there's numerous bottles in there. And each one of them has their growth medium has been optimized, I guess, to grow a different kind of microbe. So one bottle will tell you if you have sulfate-reducing bacteria. Another one will tell you if you have denitrifying bacteria, acid-forming, slime-forming. So you inoculate all these bottles, and then you see which ones show up positive, and that gives you a more specific picture of the kinds or the classes of microbes that you have in a sample. So that in itself is a little bit more useful. Now, let's talk about the good and the bad. The good points, the pros, if you will, for culture tests center largely on being relatively inexpensive, and B, being pretty simple to run, which is an important consideration. You don't need to have a lot of technical training to properly execute a culture test, unless you're doing a membrane filtration test, of course, but that's not commercially available. But the bad has some significant points we do need to acknowledge and explain. First one, somewhere in my notes I wrote down lack of specificity, but on the screen you've got not quantitative. So what we mean by lack of specificity is that by their general nature, they're not quantitative in the sense that they're designed to give you a number. The Micromonitor 2 tests, like what that person is counting in the blue gloves, they are somewhat quantitative, but even if you accurately count the number of colonies, you then have to compare it to a chart, and it gives you a range of microbial presence. So most culture tests do not give an overtly specific answer to how many microbes do I have. The second aspect about lack of specificity or quantitative, they only detect a very small fraction of the overall, what they call microbiome, the entire microbiological picture of a given environment. How small is very small? Talking about like 0.1%, 1/10 of 1%. Now, why is this? Why do culture tests only get such a small fraction of the existing microbes? Well, think about it this way. culture tests depend on the ability of cells to grow under the culture conditions. And usually the culture conditions, the conditions that they're put in after they've been taken out of their original environment, very likely those culture conditions are going to be a lot different than the environment that they came from. And so what that does is that can actually give us two kinds of variants that may develop over time. Let's say that you have a sample and you've sampled and you've pulled microbes and you've pulled some injured cells and some dormant cells. Now, the injured cells and dormant cells were not growing in the original environment, but you took them out of the original environment, you put them in a culture medium that's full of food, and they might decide, hey, I feel good. I'm gonna grow, I'm gonna consume this, and I'm gonna grow and multiply. Well, what you've got now is you now have more active microbes than you actually had in the tank because those dormant and injured cells weren't reproducing in the storage tank. You can also have cells that are actually active in the storage tank, but you put them in the culture medium and they decide, I could take it or leave it. So they don't really grow, which means they don't show up in the test, which is different from the environment they came from where they were alive and kicking in the storage tank. So lack of specificity is the first problem. Second problem is potential for contamination. And that is a huge issue with the accuracy of culture tests. See, at their heart, culture tests rely on us being able to grow a representative sample of the microbiome and to grow it in the culture medium. Now, it takes about 1 billion cells for a colony to actually be able to be visible, about 1 billion cells. And starting from one cell takes about 30 generations in order to multiply that multiply that 1 into 1 billion cells. Of course, that implies it takes time for this to happen, which is what you're giving it when you're incubating the test. So let's say that you start with 8 original microbes, right? And you've got them you're transferring them into your culture medium. But let's say that you accidentally or inadvertently, because you never know when this happens, so you inadvertently got 2 microbes in there that aren't supposed to be in there. They're from the outside. So you've got 10 total. Now, they're all going to multiply during the incubation period. But remember, not all microbes grow at the same rate. Now, maybe those 2 hitchhikers, maybe they grow faster than the others, and they grow at 2 or 3 times the rate. Or maybe they grow slower. We have no way of knowing which side's going to be the case. So after 30 generations, you got a whole bunch of microbes in there, right? But how do you know which of those microbes, those 1 billion plus microbes, how do you know which ones actually came from your storage tank and which ones came from those 2 interlopers that you inadvertently got in there? There's no way to know this with culture tests. Now, somebody could counter this by saying, well, these other tests have the same kind of problem. And on the face of it, that's true. But the key difference here is this kind of potential deviation this problem of potential deviation is inherently multiplied because of having to wait and allow all the microbes to form colonies. So instead of being able to do a test immediately and detect a 20% variance, because remember, you started with 8 microbes and then you added 2. So if you do it immediately, maybe you can detect a 20% variance. But because the culture test had that time to grow, the variance is going to be basically multiplied many times over. And unfortunately, there's no way of knowing just how bad that variance is. Okay, third thing is that it takes time. What we just talked about. A major disadvantage with culture tests, the fact that they take days to deliver results. If you're using a liquid culture, if you're using what they call a dip slide or a paddle slide, the typical recommendation is that you have to incubate it for 3 to 5 days. Well, it would be a lot more useful if you could get results in 5 minutes versus 5 days. So that's a con for the culture test as well. All right. Second category of microbe tests available in the market are what they call lateral flow devices, LFDs. Lateral flow device is a fancy way of talking about what they call an immunoassay test. Now, the word assay, that refers to measurement. Immune or immuno refers to microbes. So an immunoassay test would be a test that measures the amount of small molecules, which is what microbes are. They're small molecules or small, large. They're small organisms. Measures the amount of small molecules in a solution, and they typically do it by using some kind of antibody substance. Now, the most popular LFD, or the leading standard LFD test, is the fuel stat resonate test, developed and manufactured by Conidia Bioscience. And it has an ASTM number designation 8070, and it's what you see in the illustration. What you see is what they call a test panel. Now, each panel comes with 3 pairs of LFD modules, and they can be used to indicate either low concentration or medium concentration or high concentration of different classes of microbes, bacteria and fungi. So it has some kind of differentiation there, which culture tests do not. Now, at its best, LFDs can detect about 60% of the microbes, which is a huge improvement over culture tests, basically 600 times more accurate. And because it gives us a low, medium, high reading on these different kinds of microbes, we would classify LFDs, lateral flow devices, as moderately or somewhat quantitative, which again is a step above the indicator culture tests. Another big advantage over culture tests with these is that you can execute an LFD test and get results back in between 5 and 10 minutes, not 3 to 5 days, 5 to 10 minutes. That is a major advantage, a major check mark in its favor, so to speak. Now, what are the cons? 4 main cons that we would identify. Even though we said it's moderately quantitative, it still does not give you a specific number. It only gives you a low, medium, or high range indication. And it's also not clear what exact, in terms of meaning, in terms of telling you the exact number. They don't really have a scale that tells you, a medium indication means that you have between this and this. So somewhat quantitative, but still not as quantitative as others. Second one is that lateral flow devices can be a little bit tricky to operate. The Conidia test on the slide, it actually works like a pregnancy test. In fact, people in the industry call it the pregnancy test, the fetal pregnancy test. And so, you prepare your sample, which isn't hard to do, but you prepare your sample and you put it on the slides and you wait, and you get 1 or 2 lines that show up. And these 1 or 2 lines, so depending on the combination that you get, it's supposed to indicate a positive or a negative for that. Now, some users may find that when they look at the lines, they end up interpreting them in, shall we say, the opposite of what they should mean. It can be a little bit tricky. Even if you are paying attention, there's still, some people still get confused, even if they are really trying to pay attention to how to interpret the results. So not always straightforward to interpret. Third one, not able to be calibrated. I mean, how do you know if your given test is still good? This is an important consideration because of the fourth one, which is it's expensive. Depending on where you get them from, you're talking between $100 to $150 a shot. And so if you're going to blow that amount of money on one test, it would be nice to know that the indicator medium in the LFD is still good, because you have to store them a certain way. You can't store them like in your hot car or something like that. And so if you got a negative test, is it really a negative test, or is it just that the test panel had been deactivated and was no longer good? And you have no way of knowing, and plus you're $100 to $150 in the hole for that. So that can be a problem. All right, third option. Third option for microbial testing is ATP measurement. That is identified by ASTM 7687, otherwise known as measurement of cellular ATP in fuel and water with sample concentration by filtration. So the first test methods for measuring ATP were developed in the 1950s, so it is a technology that has been around for a little bit. Conceptually, conceptually, the test has been around for 60, almost 70 years. But the key difference here is that it hasn't always been available in the advanced form that it is now available in. Now, all ATP tests, they are all based on the fact that we know that all microbial tests have a relatively constant amount of ATP in them. In fact, all living cells in general require the ATP molecule, adenosine triphosphate. They use that in energy transportation. So ATP is present in every living cell. Now, the first ATP tests that they developed to try and measure this, what we would call first generation tests, they were the ones, depending on how long you've been in the industry, you may have seen that they almost look like ATP pens. They had kind of a pen applicator thing. And they were all right, but people found that they had specificity problems. So in recent years, they have refined the methodology. And they've been able to get it reliable enough and accurate enough that they were able to earn that ASTM designation, that 7687 number. Today's ATP testing methods, at times we've called them next generation. Now we call them Bell Performance Fuel Pulse ATP tests. These are miles ahead of these first generation pen methods. So today's fuel pulse ATP measurement test involves isolating and then measuring the ATP content in the fuel microbes that are in your sample. And the basic process to simplify is you take either a fuel sample or a water sample, you filter it to take out the microbes. Basically put in a syringe, you got a filter that fits on the syringe, you push it through, it's filtered out all the microbes in that sample. It's also filtered out a bunch of other stuff that aren't microbes. So what are you going to do about it? Well, you have to wash the rest of that stuff out. So you take a special solvent, you put it in there, you push that through. That actually washes out all of the organic, non-microbial stuff. And so now you just got microbes in that filter. You then use a couple other solvents to actually extract the ATP. Essentially, the microbial cells will actually burst open, and the ATP will be washed out into a diluting liquid, which can then be combined with a small amount of this special enzyme. And what the enzyme does is the enzyme, by its nature, actually causes the ATP to actually glow kind of like a firefly. It glows when it's exposed to UV light, okay? So you take the sample and you put it into this special machine called a luminometer, and the luminometer measures the light glow when it exposes it to light and gives you a fairly accurate measurement of not just whether you have low, medium, or high, but the actual number of living microbial cells in the original sample. So, just as with the other tests, we've gone over the pros and the cons. We're going to do that with ATP testing, but we're going to flip it around. We're going to talk about the cons first, the bads. The first one that I would do, and as somebody who has run hundreds of tests, I am intimately familiar with the pros and the cons. So the first one is that the methodology for this is a little more technical than the other options. It requires specific equipment like the luminometer, and it is a multi-step process, and you have to follow the process in order for the test to give you the results that you need. Now, having said that, we don't want it to seem like it's something that you need a PhD to do, which is absolutely not the case. We want to soften this negative a little bit by saying that in our experience, all that's needed to overcome this is some training for whoever's doing the test. And what we mean by this is once you explain how to do it, and you do it like 3 or 4 times, that's all it takes. The technician or whoever's doing it, it's all downhill from there for them. All right, the second one is that you do need to be careful when you're doing it. It means you do need to pay attention to executing it properly. Now, I deem this the fact that ATP testing is process specific. It's my way of softly saying that you have to pay attention to what you're doing because the process is a little bit technical, as we said. Things have to be handled carefully in order to prevent contamination of your samples. However, again, same solution. Once a technician executes the tests a few times, it becomes relatively simple to do. It just looks complicated from the outset. So that's the bad. We always want to have full disclosure, and if we were fully disclosing what the good and the bad are about fuel pulse ATP tests, that's what we would say. But now we have to concentrate on the good because there are some really significant advantages that set ATP testing apart from the other kinds of microbial tests. And these are big advantages with respect to accuracy, specificity, and speed. So, accuracy. Remember we said that lateral flow devices detect about upwards of 60% of the microbiome. Culture tests only do 0.1%. ATP tests, fuel pulse ATP tests, detect about 70% of the microbiome. That means that the ATP test is at least 700 times more likely to correctly detect microbial contamination than, say, a single culture test will. Specificity, number 2. ATP testing, fuel pulse ATP testing does not give you just a range, a low, medium, high, or a yes/no reading. Fuel pulse ATP testing is designed to give you a specific measurement of the number of microbes in your sample, which has obvious advantages that cannot be overstated. It's a huge advantage. And then the third one, speed. Similar to the lateral flow device, ATP tests can be performed in the field if you've got the right equipment. I mean, you could perform it next to the tank if you had the equipment with you. Usually, though, we do it in a lab, in an indoor setting, and a single test can take only 4 to 5 minutes. Boom, you get results. And this is a huge advantage because, the feature, specificity and speed, those are critical advantages that ATP testing has over the other microbial testing options. So if you take that and you relate it to what you're doing, if you're a fuel manager or an operations manager and you have stored fuel, and think about the advantages that those two things would give you with respect to giving you the information that you need to take the right course of action for your fuel. See, a fuel manager could pull a fuel sample. They could execute or have somebody execute a fuel pulse ATP test at their facility, and they get the results back in like 5 minutes. And let's say that the results are clear. They have a high microbial contamination of X. Let's say they have 200,000 microbial units per milliliter, which is a solidly severe contamination. Now, depending on their situation, and if they've been doing any kind of trending, they can compare that number to their previous results. And they now have a lot better information to make a decision on whether they need to take action immediately instead of having to wait 5 days to get some kind of general you may or may not have a problem kind of information back. And then there's another option. Let's say that the operations manager makes a correct decision to treat the stored fuel with biocide, to clean it, to try and knock down these microbial levels. So they administer a solution, they do everything like they're supposed to, and then they're done. Now, so they take a step back. They're satisfied with the fact that they were able to know what they had to do. But how do they know that the problem's solved, right? How do they know that it's solved versus not solved? The easy answer here would be you do another microbe test. 5 minutes later, he gets the results back, he or she gets the results back, and now instead of 200,000, they've got 4,500. Well, boom, I'd say that problem is solved. They could not do that with any other kind of test. They could not do it with a culture test. It would be really hard to do it to that level of specificity with a lateral flow device or a microbe monitor or a liquid cult. And if that kind of picture relates to you, I think you can know inherently the value of what we're talking about there. So given what's at stake with today's fuels, especially stored fuels that power mission critical systems, all of this kind of thing is a huge advantage. And in our view, this is what sets this kind of ATP microbial testing apart from all of those other options that have been available to them. Now, one of the takeaways from looking at microbial testing options here is that we have to keep a proper perspective on the accuracy and the meaning of the test results that we get. Now, this is because a positive or a negative test may not tell us the entirety of what we think it's telling us. Now, let's unpack that a little bit. Now, let's take an example. Let's say if you do a culture dip slide, a culture test like a dip slide test or what they call the paddle test, you do one of those, and it comes back negative, okay? You don't have microbes. Do you know for sure that it means there are actually no microbes in the tank? Well, if not, then what are the possibilities for why it's not telling, or why it doesn't tell us that? Since the culture test was done on a fuel sample, right? You had to take a sample to do it. So you took a sample and then you did a culture test on that sample. But what if that sample was not representative what if it wasn't a good representative sample? So the conditions of the tank are different. So that means that the sample's wrong, and that meant that that was a reason why your results were wrong. And a culture test, because the culture test only detects a small fraction of the microbes, maybe you did actually have a good sample, but the test that you selected was not specific enough to actually show us the microbial presence that was present in your tank. So when you have a negative microbial test, it can actually mean one of three things. The first one is you got what we would call the wrong sample. That means you really do have microbes in your storage tank, but your sample didn't capture them, and therefore any testing on that sample gave you the wrong results. It could mean that you have the wrong test method. That's what we were alluding to with the dip slides. It meant that, there's actually microbes in the sample. I mean, we got a good sample, but the test method did not detect them. So that's a problem too. Or you could have right sample and right method. Means that your negative is actually correct. Your system actually is uncontaminated. Your negative test result is valid. Now, we have spent time alluding to the limitations of culture tests and lateral flow devices, things like that. We do have to apply the same proper perspective to ATP tests. Remember that even if you get a number back with an ATP test, you have to have proper perspective on what that's telling you. So with ATP tests, you get a number back. It's number of what they call MEs, microbial equivalents. And what that basically means is number of microbes. So you get a number back. Now, typically when you get a number back, you have to interpret that. You're interpreting it to try and say, does this tell me that I have a problem or not? And when we do this kind of analysis, depending on what range of number it is, it gets a red or a yellow or a green designation. But we know that even though red, yellow, and green colors are intended to imply that a microbial level is moderate or severe or not, either of those, we have to remember that what we've got is a total microbe count. And not all microbes are equally problematic. Remember earlier we talked about, this is a microbial world. We're just living in it. There's microbes all around us, which means it's impossible to have a microbe-free situation virtually anywhere, which means the goal is not to be microbe-free. It is to have a manageable level of microbes. And so we said, well, what's a manageable level? And we said, well, that depends on what the levels are. Specifically, what the levels of the problematic microbes are. We know, let's say you have 1 million microbes. We know that 1 million microbes of one kind are not necessarily equivalent to 1 million microbes of another kind, or even 10,000 of another kind, from a will it cause a problem standpoint. So not all greens and not all reds are created equal. It's a total number, but it doesn't tell you all the different kinds that are in there. And whether that number is going to cause us a problem depends on the composition, the microbial composition that's making up those greens and those reds. Unfortunately, just having said this, we're now going to take a step back and we're going to say we don't have the ability to actually know that, to get as granular as that. So we have to go with the best information that we have, which is the total amount, and we have to make the best decisions that we can based on what we think that's telling us. So that is a brief consideration of the main testing options here. For stored fuel, the goal is to detect and measure if you have a microbial content, a certain level of microbial content present. And then based on those results, you can then transition from condition monitoring and condition testing to this thing called contamination control, which is controlling and getting rid of the problem that we think we have. Now, I think we're bumping up on about an hour 20, and typically we like to keep these things as close to an hour as possible, but really there's so much content here that we knew we were going to have to go over a little bit. So we're going to try and get through these last parts as quickly as possible. Let's get to it. So to this point, we have, or at least we assume, that we've sampled properly. If we were paying attention during the condition monitoring webinar, we know what to do there. We have tested. We hopefully have interpreted the information correctly. And we may have come to the conclusion that there's a microbe problem that requires remediation. This is when we have to look at contamination control, what we have to do to get rid of the microbe problem that, if we don't do anything, is going to destroy our fuel eventually. Now, the three most common microbial contamination control actions are dewatering, tank cleaning, and chemical treatment. Now, we said that microbes do not need very much water to do what they need to do. Now, if you have a bulk fuel tank and you have a free water phase, you know that you have to get that water out of there. So you try and get it out of there. And let's say you're able to get all but the last 1/8 to 1/4 of an inch of water. Anybody out there who has tried to do that knows exactly what I'm talking about. So let's say that you only left like 2 gallons of water in there. Now, remember earlier that we said in bottom water, every milliliter of bottom water can contain up to 1 billion microbes. So if you have 2 gallons of water, tucked away in a corner somewhere in that tank, you've got enough water in there to support 8.5 trillion microbes. So it is really important to get as much of the bottom water out as possible. but you know that you're not going to be able to get all of it. And because the bottom water has so much concentrated microbial presence, this means that we need to do more than just removing the water if we hope to really solve the problem. So that means tank cleaning. Now, man-entry tank cleaning is going to be the gold standard for this, but not many companies have the ability or the desire to really do this. So we do the best we can with external tank cleaning. That's what companies, fuel polishers and fuel treatment companies, service companies rather, they will not do man entry into the tank. They will use stingers and suction and hoses to try and suction and remove as much of the biofilm and, of course, as much of the water out of the tank as possible. Now, removing as much sludge and biofilm as you can, that is essential to contamination control, because biomass, first of all, we've already said that microbes love to live in biomass. They love to live in biomass. It's their favorite place to live. And if they're living in biomass and you put a biocide, a chemical, in the fuel to try and kill them, well, the biocide is not going to reach them. They're going to be shielded. And if you have a lot of biofilm, then it only increases the chances that your biocide treatment that you're doing, expecting it to kill all the microbes, there's a good chance that it's not actually going to be fully effective. Now, just like with water, it is really hard to get all the biofilm out of that tank, especially considering, let's just say, the limitations of where you can reach. But you need to try and get as much of that out as possible. So you want to remove as much water as possible, and you want to remove as much biofilm or much biomass as possible. We've already acknowledged that it is virtually impossible to get all of that out. That makes chemical treatment that much more important. Now, in previous webinars and trainings, we talked about the aspects of what makes a good biocide. And for the interest of time, we can't rehash everything here. Bell Performance and in Bell Fuel and Tank Services, we have two different chemistries that we use. One is Bellicide, which is thiocyanate, and one is Bellicide ISO, which is isothiazolone. Both of them are excellent, what they call broad-spectrum chemistries, which means they do well at killing lots of different kinds of microbes. They're both very good chemistries. We'll just leave it at that. Now, so and that's an important thing. You have to start by having an actual effective biocide chemistry. Once you have that, you need to use it properly. Biocides need time to work, and that period of time is typically what's referred to as a soak time. Now, how long, how much soak time do they need? Well, if you ask the fuel microbiologist, he would say, well, 24 to 48 hours is an optimal soak time. Now, that's if you're like a fuel service company, you may not be able to wait 24 to 48 hours, but if at all possible, that is your optimal window. If you have a smaller tank, maybe you can cut it down to 12. Then, of course, if you have a moderately or a heavily infected system, you would then expect to have plugged filters. Once the microbes are dead, you would expect to have those until the dead microbes and the biofilm have been flushed out of the system. So this leads us into this, the caveat. Not all tanks are the same. Now, this is important. At Bell Performance with Bell Fuel and Tank Services, we always try to give the straight story to our customers, because we know that if you don't, it's just going to come out and bite you. And this is something that we wish this were not true, but since it is true, it's worth talking about. In the rush to simplify things or oversimplify things, sometimes there's a disservice that's done to the customer. This disservice is when it's implied that all solutions are just one size fits all. And what we mean is that when it's implied that no matter how bad the extent of the infection in the tank, no matter how bad the amount of biomass that's in there. One shot of one biocide is going to cure everything all day, every time. Now, that is, when I said not all tanks are the same, let's just say that that's not always the case, right? There are certainly cases where one tank may be more heavily infected than another tank. So if you have one tank that's got twice as many microbes in it than the other, why would you expect the same amount of biocide to kill both of them equally effectively? You wouldn't. So there are certainly sometimes some cases where you may need to treat a tank again to ensure that the problem is wiped out. Not all tanks are the same. Not all microbial infestation problems are the same. Not all contamination levels are the same. And even though these biocide chemistries like Belicide and like Belicide ISO, even though they are broad spectrum, not all kinds of microbes respond exactly the same to every kind of chemistry. That is why it is so important to do things like condition monitoring. Without condition monitoring, without having a tool like ATP testing, without those, you are only guessing at whether you've actually solved the problem. So the possible need for multiple biocide applications, many times that hinges on the level of contamination. Sometimes there are tanks that may require 2 or even 3 applications. 3 is relatively rare, but sometimes you may need to do a second application. How would you know when you need to do this? Only if you're utilizing something like field pulse ATP testing within the context of a good condition monitoring program. Only doing that kind of testing can you determine if the microbe levels after treatment have actually been reduced to your desired level. And then finally, remember we talked about the fact that microbes can be shielded by biofilm. This is where if you pair a biocide with a biomass dispersant like tank treatment SDF, that's when that can be useful because the biomass dispersant will actually break up the biomass, make it easier to remove, and increases the overall effectiveness of the biocide, which then reduces the chances that you're going to have to end up treating the tank a second or a third time. So we have reached the review slide. We have covered the bulk of what we need to cover. So typically, we just do a quick review. So let's review what we have covered so that we can wrap this up. Covered a lot over the course of this webinar on condition testing and contamination control options. Hopefully, besides more than a few useful tidbits about field microbiology and a broad realization of how complicated things may be than what we first think they are. Hopefully, besides those things, hopefully you will have been able to come away with some useful main points. So we started, of course, with a review of the importance of condition monitoring, which was the subject of our previous webinar. But it was worth reviewing because best practice condition monitoring and best practice testing, they both go hand in hand. Once you have your representative samples from your condition monitoring, you have different testing options to help you answer the right questions that you're going to be asking about them. What's the condition of your stored fuel like? And does anything hint that you have a current or a future problem? Things like gross observations, sight and smell observations, those are a good, easy starting point. Even though they're not intended to be fully quantitative, they do have definite value. You have chemical and physical tests that give us ASTM-rated measurements of specific fuel properties that may be important for telling us the current state of the fuel and as well as being predictive about whether there might be a problem with the fuel that's coming. And then we spent the most time on the microbiological test. And that was appropriate given that microbiological contamination is the number one problem facing stored fuels today. Plus the fact that stored fuel users have more options in this arena than they ever have before, but not all of those options are good, as we learned when we discussed the pros and the cons of culture tests versus lateral flow devices versus liquid cults and micromonitor 2s, and once the smoke cleared with all of that, we should have come to the conclusion that ATP microbial testing, like Fuel Pulse, is the most useful and the best option for stored fuel users. And then once you have identified a microbe problem, you're not going to get rid of it without proper application of biocide, which involves applying the right amount of biocide, making sure it's well blended into the fuel, and employing or giving it the proper soak time to give it time to work and kill everything off. So ultimately, microbial contamination control in stored fuels is a never-ending process. It requires us to pay attention, both to prevent it and to fix it when we find it. Hopefully, today's webinar brings you at least a couple steps closer to being able to do that. If you have any questions about any of the content or any of the suggestions that we presented today, my contact information is on the screen. You can email me here at ebjornstedt@bellperformance.net. We understand that all of this is complicated. It's a complicated issue. Sometimes it's helpful to talk to someone who can give you some guidance or, maybe even partner with you to solve a problem if that's what you need. Now, if you recognize that, if you think that you're in that position, then please drop me a line and we will get you the help that you need. You can also check out the Bell Performance website. We've got lots of information there on best practices for maintaining stored fuel, especially if you go to the section that's labeled our Bell Fuel and Tank Services section. So I want to thank everyone for joining me for this rather long webinar today. We went a little bit longer than we normally do, but we had a lot to cover. So again, thank you for joining me today. I am Eric Bjornstedt. I'm the Technical Information Director for Bell Performance, and this has been our Bell Performance webinar on condition testing essentials for stored fuel. So we will see you next time. Bye-bye.